today we'll be talking about one specific product that we have that basically allows you to work with TypeDB in production and enterprise setting. And specifically, we were going to talk about one aspect, which is probably the most interesting aspect in building the software, which is the fact that it is a distributed database, right? So we're going to take a look into how the whole thing was built, and also like specifically the main algorithm that we use to basically perform the data replication. So let's start with the initial product that we have, which is TypeDB, right? So TypeDB is a database software that allows you to create a and model complex data and reason over it. An application that leverage TypeDB would enjoy the benefit of being able to create to run in a correct and efficient way, provided with the strict yet expressive query language, which is TypeQL. So in development, you'll be able to create an application in a productive manner that is correct and efficient. But when you take that application all the way to production, you will be facing different kinds of problems that you still need to solve, namely security and scalability and various deployment issues, as well as scalability. So how do you deal with this? So in TypeDB is a database software that only works as a single server. And what happens if you need to scale out? What happens if, say, the server crashes? Because you don't want your business to stop running just because the server crashes, right? And in this slide, I've shown you the typical deployment of application that runs on TypeDB. Obviously, there will be like one or more applications that connects to a single TypeDB server, right? And in TypeDB Cluster, which is the other flagship product, we are going to run the application in a slightly different configuration. So TypeDB Cluster is meant to not only tackle complexity, but also does so at scale, does so at production systems that needs the application to be robust and performant. So for example, it will be possible for you to run multiple instances of applications connecting to the whole set of servers running as a single cluster. So in this configuration, you'll be able to enjoy scalability and availability. TypeDB Cluster is scalable because the more servers that you have in the cluster, the more performant it will be, because it'll be able to respond to more read transactions the more servers you have. And it is highly available because the more servers you have in a cluster, then the more failure you can tolerate. And therefore, with this setting, you will be able to benefit from the availability and scalability benefit that makes your application not only robust, but also performant. And not only that, all of these features are provided in a way that's automatic. And what I mean by that is it requires minimal user or administrator intervention, where, for example, if one of the server crashes, then the cluster will continue to operate where they know how to mitigate the failure by coordinating the remaining servers to talk to one another to still run as a fully functioning cluster. Now let's make a room to basically simplify the example here. I'm going to make the servers a little bit bigger, and we're going to take a closer look at this particular example to explain the concept of cluster and server and replica. So let's take a look at this example where you have, say, a typical application running on a cluster with 3 servers, and you have 2 databases, DB1 and DB2. Let's say, I don't know, this application is like a typical, say, front-end application like a fintech or like an e-commerce of some sort, right? So the databases, right, in the clustering model will have its own copy on all servers. So in this case, the DB1 and DB2 all will have one replica on each server. So DB1 will have 3 replicas on server 1, server 2, and server 3, and DB2 will also have the same number of replicas, each on one server. Now, replicas play distinct roles between one to another. One replica will be designated as the primary replica, whereas the other replicas secondary. And each database is running on its kind of like own replication group, which means that, for example, the primary replica of DB1 will sit on the first server on the left, whereas the primary replica for DB2 will sit on the server on the right. So when the user uses the TypeDB client to connect to the database from the application, right? Let's say it's going to open, it needs to open a typical read or write transaction. These operations are served by the cluster in a strongly consistent manner, which means that it's going to be really easy for you to reason about, as opposed to, say, other kinds of clustering model, such as eventually consistent model, where you may have to think whether the data that you get is the most recent or not, right? In TypeDB cluster, everything is strongly consistent, and by default, all operations that you do is executed on the primary replica, ensuring strong consistency. So in this case, the application is performing a transaction that goes to the primary replica of DB1, which sits on the server on the left, or server 1. And similarly, if the application needs to talk to DB2, then the application will communicate to the replica that sits on server 3, given that that's the primary replica for DB2. So we'll take a look at why and how the application can decide to talk to the right server later, right? But for now, it's safe to say that these operations will be done automatically by the client without any intervention from the user. So basically, the user simply needs to use the TypeDB client like usual, and the client for cluster will have its own mechanism to know which server should it talk to. If, let's say, the first server crashes, when that happens, obviously the replica on the first server will no longer be accessible. So when that happens, the application will know to basically transition when trying to connect to DB1 from server 1 to server 2. And all of this, these failover operation is also done automatically without any user intervention. So there is no need for the administrator to log into the application and change the configuration to set the primary IP address from server 1 to server 2 or anything like that. All of this will be handled automatically. Now, we've taken a look at the typical read and write operations and how they're strongly consistent, meaning that you always see the latest version of the data, which is really nice because it's really easy to reason about. Anything that you see is always basically the final version of the data without having to think about it. However, that does come with a cost, which is it places a lot of load on the primary replica. Whereas the secondary kind of does nothing except to act as kind of like a backup, as a backup that may be activated if the primary dies. So there is an additional mode for read transaction that you can leverage in this case to allow you to actually utilize the other servers a bit more to basically optimize the utilization. And in this mode is what we call as the read any-replica. When you're opening a read any replica transaction, unlike the regular read transaction, the query may be performed on any of the replica and not just the primary replica. So again, the client will know how to load balance between all replicas to achieve maximum throughput. The benefit is obviously you get basically as much throughput as the number of servers you have, but the drawback that you will have to pay is the fact that the data that you're seeing might not be the latest incarnation of the data. So it's a trade-off. When you're dealing with, say, the user's bank account, then you might want to display the most consistent version of the data, which means that you want to basically use the default read replica, the default transaction read. Whereas for, say, getting the average numbers of users that's running within the given hour, probably you can tolerate a bit of staleness, and this would be a good primary use case for the read any replica. And read any replica would be quite useful when you have lots of rules which are expensive to compute, and you might want to basically increase the throughput by running the query not just on the primary but also on other servers. So what we've kind of like insinuate is that the application somehow knows to talk to the appropriate replicas, which is located in a particular server. So how does the application do that? And this is the question that we're trying to answer in this section. So the application obviously uses TypeDB client under the hood, and basically the TypeDB client is the same TypeDB client that you are probably already familiar with when using TypeDB, except that the client actually has two kind of like modes. One is the TypeDB client, and the other one is the TypeDB Cluster client. And when you activate the TypeDB Cluster client to connect to TypeDB Cluster, there are basically additional mechanisms that they add to allow for ease of use, allowing to automatically fail over or load balance between these servers. So in this application, right, we have the TypeDB client, and the application wants to connect to the cluster with 3 servers, DB1 and DB2, 2 databases, right? And basically the automated failover and load balancing feature is what we call, is how we call it, right? Basically, it's done by exchanging data between the cluster and the client. And for example, when the application needs to connect to the cluster, right? Let's say we have 3 servers within this cluster. The application actually does not need to know about the existence of all servers. And instead, the application can just be told about the existence of, say, 1 or 2 servers. And when trying to connect, the application will exchange data with the cluster to discover all servers that exist within the cluster. So you can simply give the IP address of, say, server 1, and when TypeDB client tries to connect to server 1, then server 1 will reply, oh, by the way, in this cluster, I have some other servers. Here are the IP addresses. And then the client will say, oh, all right, cool. So not only now I know that there is you in the cluster, but I also know that there are 2 other servers, right? And I can use this information to appropriately connect to the right server, given the kind of query and the target database that the user needs. So in this case, for example, right, then the application, given the IP address of, say, server 2, will now know about the existence of all servers and can perform the right transaction to the appropriate database. If it needs to perform some update to the user account balance, then it would need to connect to the primary replica of DB1, for example, whereas when it tries to count the number of, say, active users in the past hour, it can connect to the secondary replicas of DB1, which exist on server 2 or server 3, respectively. So in conclusion, what's cool about this is basically the abstraction over connecting to the cluster the fact that you don't need to know about the existence of all servers, it's going to be completely transparent, much like when the application just needs to connect to a single server in the case of TypeDB. So literally, there's no need for you to manage the configuration on connecting and load balancing. Now, moving on to the more intricate manner, which is how do we get the data between all replicas to be replicated in a safe and robust manner, and also performant manner, obviously. And this is essentially the typical distributed systems problem. You have many servers and you need to replicate the data between them. We need to start with the right assumptions, which is, for example, will the server be always on, right? Well, the answer is probably not, because servers go down all the time. You don't want the data to be corrupted just because the server happens to crash, just because, for example, the server doesn't have enough memory. The network will also not always be available. Sometimes the network gets cut off because maybe the firewall settings are changed in the incorrect way by the administrator, or maybe the cable gets pulled, or maybe the router gets disconnected and all that, right? So these things happen on a day-to-day basis. Well, maybe not on a day-to-day basis, but like at least once a month, these things will happen. And you want guarantees that the database can perform despite these failures. And these things must be done in a way that doesn't rely on global coordination as well, because it's actually really hard to, hold on a second. Oh, there's a question. Okay, Matthew, I'll try to answer your question later. Let me just move on with this. So where was I? Oh yeah, the global coordination. So in a distributed system, it's really hard to perform a global coordination in a centralized and reliable manner, because as we saw before, servers may go down, networks may get disrupted, and you can't really done global coordination in a centralized manner, because then there is a single point of failure, which is the system that does the coordination. And TypeDB Cluster is designed to not depend on any central server to stay alive in order to maximize the availability of the system. And this is done by a specific component that we've introduced in TypeDB Cluster, which we call the replicator. And replicator is our Raft-based replication engine, which is built to be efficient and robust, which is based on the Raft replication algorithm. I don't know how many of you are familiar with the algorithm, but basically it's an algorithm that allows you to perform data replication in a safe manner. And the theory behind Raft is actually quite sound, quite mathematically sound, and has been proven and tested using various kinds of theorem provers, such as TLA+, right? There are other algorithms that sits on the same category as Raft, such as Paxos. Obviously, there are so many variants of Paxos, which we're not going to discuss over here because we're going to be focusing on Raft. And finally, the replicator engine is basically built using Java, relying on other battle-tested technologies such as RocksDB and ZeroMQ, amongst others. So we're not going to be focusing on ZeroMQ or RocksDB, but today we're just going to be focusing on the Raft algorithm itself, and we're going to explain to you the basic concept and what makes it tick, right? So that it's clear why and how these systems work the way it should, despite failures that may happen in the network or in some of the servers. So the key, before going deep into the way Raft works, the key aspects of Raft is that it guarantees correct data replication despite server and network failure. And what that means is if you have some set of data that you need to replicate, right, between many servers, then you can basically start writing the data into one of the server, and then data will be replicated via the network. And no matter whether you, for example, pull the network out or basically shut down the server in an abrupt manner, when the operation is resumed, the replication process will then start resuming from the last checkpoint without any risk of corrupting the data. And that's actually really cool because basically it literally doesn't fail even when, for example, midway through replication, you basically plug the cable of the server. And this safety is achieved by two primary means, which is the leader election and the log replication mechanisms. So let's take a look at these two mechanisms, starting from the leader election. So what does it mean for a leader to be elected in this system, right? So if you remember previously, we were talking about the way TypeDB Cluster works, where you'll have database replicas and how one replica will be designated the primary and the rest will be designated as the secondaries, right? So this is actually something that that is based on Raft. And in Raft, each instance, each replica will either play the role of the leader or the follower. So the leader instance will obviously be the primary replica, and the follower instances will be the secondary replicas. And the leader election mechanism is a specific mechanism that guarantees that there exists a single active leader at any given point in time. So notice that I didn't say a single leader, but rather a single active leader, because as I'll explain later, there will be scenarios where it's possible for the system to have several leaders all at once. Okay, so in this example, in the screen, we have a cluster, again, with 3 servers, and we have a single database here, and the database is managed by the replicator instances. We have 3 replicas for the database, and each replica is managed by a replicator instance that exists in the server alongside the replica. And let's say when you boot up the server for the very first time, right, the replicator engine will get booted up, and they will all start running in the follower mode. So none of the replicas are leader at the moment. Now a follower will try to see if there are any active leader. And when there isn't, a follower will start to think that there might be an election that needs to be run. And this is governed by something that is called the election timeout. So essentially, a follower will wait for a specified amount of time before it becomes impatient and think that an election is due. So each replicator will have an election timeout, which is randomized. So they're not all the same. They're randomized, say in this case, let's say the replicator is configured to start an election anywhere between 300 milliseconds to 700 milliseconds, for example. And they're randomized in order to minimize the number of parallel concurrent election happening at the same time from multiple replicators. So basically, in the most ideal scenario, there is only one replicator that starts an election at any given point in time. When there are multiple elections happening at the same time, it will not affect correctness. However, it will make the process less efficient because then the vote might be split and you might need to run another election in order to decide who's the leader. So in this case, the election timeout of the first server is 500 milliseconds, the second server 300 milliseconds, and the third one 700 milliseconds. And what that means is that the second server will most probably run the election. And when that happens, within an election, the follower will become what is known as the candidate to become a leader, right? And in this case, basically, the secondary will propose for itself to become the candidate of the leader. And this is part of the election process. The election process is actually quite simple. It's not like the real election where anyone can vote for anyone else. In Raft, anyone who starts an election always propose itself to become the leader. So there's never going to be a scenario where, say in this case, the second server, when it reaches the election timeout, will continue to propose, say, the third server to become the leader. No, that's not how Raft works. So in Raft, anyone who starts the anyone who runs out of the election timeout will propose itself to become the leader. So there is a number besides the follower and candidate, which is 0 and 1 respectively, and that is what is known as the term number. And the term number is something that's really useful, which I will explain later. But in this case, let's continue with the process where the second server starts an election and opts itself to become the candidate. So the second server will communicate this candidacy to the first and third server by sending a message. And any follower that receives a proposal from a candidate in Raft will always accept that proposal. So again, this is unlike the real election, in which if there is a candidate, then you may opt to either vote or not vote for that particular candidate. In Raft, it's much simpler, where anyone who first starts an election, if I'm a follower, I will immediately grant my vote to that candidate. So given that the second server starts the candidacy process, announce it to the first and third server, both servers will immediately reply with a vote, right? And the second server will become a leader, not when it receives a vote from all servers, but rather only from the majority. So what that means is the second server, in the scenario with 3 servers within the cluster, only needs 2 votes instead of 3 votes. So the second server, obviously, by announcing candidacy, is essentially voting for itself. It only needs 1 more vote from either server 1 or server 3 to become the leader. And this is actually quite an important property, because what that means is if, let's say, any of the server goes down, right? Let's say the third server goes down, then the second server will still receive a vote from the first server and can still become the leader, continuing the operation. And this is as opposed to needing the vote from all servers, which is not flexible, because then if any of the server goes down, then the leader election process will not continue. So this property of being able to elect a leader by requiring a vote from the majority instead of from all servers is quite key to the availability aspects of Raft, in which it can still continue performing the election successfully, even when a few server is unavailable. So continue with the process. The second server has become the leader. increase the term number from 0 to 1 communicates the leadership back to the followers. So basically, this is the leader confirming that, yes, I did get a vote from you, but just FYI, I also get a vote from other servers, which form the majority, and therefore now I can confirm that I am the leader. And therefore, here's the confirmation, and here's the information of the term number in which I'm the leader of, which is term number 1. So that's about it when it comes to the leader election. And what's cool about it is the idea is actually quite simple. Anyone can start an election and anyone votes for itself, and any other servers that hears from the leader will immediately grant its vote, right? Quite a simple idea, but they work despite failures that may happen in the servers. So if one of the server goes down, the whole process can continue. If, let's say, the second server, which is proposing itself to be the candidate, actually crashes midway as it's proposing itself, then the algorithm will actually still continue to work, because what's going to happen is then the first and third server will stop hearing from the leader, from the candidate, right? And then we'll start the election timeout again, and either the first or the third server will start a new election term, which is election term 2, and attempt to become the leader. So in conclusion, the idea works despite any arbitrary failure that may happen at any given point in time during the election process. So given this robust step in which one can elect a leader, right? Let's move on to take a look at the data replication process. So let's make a bit of room within the database of each server. I'm going to make it empty, right? And we're going to explain the components that make log replication work. But before going into that, let's understand the big idea about log replication. So whereas the leader election process guarantees that a single active leader is elected, no matter whether there is a failure that happens midway during the election process, the replication process also guarantees that the data can be safely replicated from the primary to all secondaries, again, despite any crashes or any network disruptions that may happen in the cluster. So specifically, the guarantees are that the writes will be eventually be replicated across all replicas, and the writes will be executed in exactly the same order between replicas, because obviously if the writes are executed in different order between different replicas, then it's going to be a big problem, because that may lead to data inconsistency, right? So this thing is also guaranteed by Raft. And a nice property of this replication process is, again, if any of the server goes down, the replication process can continue. Let's say you're in the middle of performing a replication to all 3 servers, right? If, let's say, at that particular time, the second server, sorry, let's not use second server because it's the leader. Let's use the third server. If the third server goes down, then the primary can still safely acknowledge the data, given that it's been replicated to the first server. And it can continue resuming operation, serving the application. And eventually, when the third server is brought up, it will resume receiving the data that it missed during the time it went down. So these are the guarantees that's provided by the replication process. And now that we've understood the goal and the guarantees of the replication, let's take a look at how it is achieved under the hood. So the replicator is a component that manages the database replicas, as we've known. And one key important component within the replicator is what is called the replication log. So the replication log is, it kind of works similar to in accounting. Like, I don't know how many of you are familiar with accounting. Like, I'm not really familiar, to be honest, but I know that they have like this ledger where, you know, like if you, the ledger basically keeps track of the changes to the balance, right? Let's say instead of storing my balance as like 50 bucks, right? I'm gonna actually store the changes that it's made to my balance, which is rather than storing the number 50, it's gonna store 10 plus 10 plus 10 minus 5 plus 5 plus 10 plus 10. So it keeps track of the activity rather than the final value. And that's actually quite similar to how the replication log stores its activity. So when an application performs a write operation using write transactions, right? For example, it does an insert $P if a person has name Bob, then this query or this activity will be stored in the replication log. This is a simplified version because we're actually not storing the query. We need to store it in a completely different way, but conceptually, it's as if the query is the activity that we're storing, right? So we're gonna perform a query to the primary, which in this case is server 2, right? And this query or this activity will be stored in the replication log, and the leader will try to replicate this activity to the other remaining secondary replicas. So it's going to continue trying to replicate to server 1 and server 3. As I said before, if one of the server goes down, it's still going to continue because let's say, for example, if server 1 crashes, right, then the primary, which is server 2, can still continue replicating to the second server, which already forms the majority because if the data is stored within the second server and the third server, then essentially it's already considered safe to be acknowledged to the client. And then server 1, when it goes back up, can receive the activities that it missed during the time it goes down, right? And similarly, if let's say the primary actually goes down, right, then it's still going to be safe to continue because then essentially the first and the third server, which are both followers, and by definition a follower cannot accept or write operations, right? The first and the third server will simply run the election process again to elect the leader, a new leader between one of those, right? So at some point, when this data replication process has been safely performed and has been stored to either the majority or all servers, then the data can finally be committed to the replica. And in this model, right, basically, oh, I have more questions coming. All right, let me just finish this. In this model, basically the data will be stored in the activity log, right? And as I said before, what's cool about this model is one of the key properties of the activity logs is that it stays completely in sync and identical between one to another. So the activity log of the first and the second and the third server will all be exactly identical. And essentially, Raft is what we call the state machine replication algorithm, which means that it doesn't actually, like the Raft algorithm is meant to be used as a data replication mechanism, but we don't actually just replicate the data, but instead we replicate kind of like the diff of the data or like the activity that may produce that data. Like in this case, we're actually, for example, replicate the kind of like the query or the activity that may then be executed on the on each replicas to perform the final state of the data. So replicated state machine, given identical initial state and given the same steps that are performed on each machines, right? If they're deterministic, then you will end up in the same state between across all machines, across all replicas. So at some point, this process can simply continue, and you will have more activities being performed. These activities will be recorded in the replication log in the same order and will be executed across all servers in the same order as well, resulting in consistent final value between all replicas. And what's cool about this, again, is, as I said before, this works no matter what kind of failure scenarios that may happen. If one of the secondary goes down, then the remaining servers may continue to operate. If the primary goes down, then the remaining secondary will go back to the election process and elect a new primary and continue operating with the remaining servers. If there's only one server that goes up, then the primary will one server that goes up, then that server will simply reject the operation back to the client, saying that I cannot proceed in this state because most of the server in the cluster are unavailable. And it is done so because it is unsafe to continue receiving operations when the majority of the servers are unavailable. So basically, with the Raft algorithm, you can tolerate a failure as long as the majority is still running. So in the case of 3 servers, you can tolerate 1 failure. In the case of, say, if you have 7 servers, then it's going to be much better, because then you can tolerate up to 3 servers failure, 3 server failures. And when the failure becomes too severe, then Raft will simply stop receiving operations, ensuring that there is no unsafe operation that is performed to the server that may lead to inconsistent data. So we've taken a look at TypeDB Cluster and how it kind of like works as a distributed database as a whole. It's a database that's based on Raft for its distributed data algorithms. It uses this unique client server fault tolerance and load balancing to allow automated failover and data load balancing between the servers without any interruption from, without any manual intervention needed in case of failure from database operations, which is actually quite cool, because like nobody wants to do manual work when it comes to recovery because it's error prone. And then also we've touched into kind of like the high level understanding of the data replication based on Raft. Raft is quite a simple algorithm, I would say, conceptually, but it is definitely very subtle. So I did not touch on many aspects on the basically the edge case failure scenarios that may happen. Right, I only touch base on the most common failure scenarios. So any questions, definitely just pop into the chat box and I'll read them and try to answer them. And yeah, there will be more innovation coming, such as the backup system that we haven't built, which we will build. Geo-replication, which is also something that we haven't built, which we will build in the near future as well. But for now, that's it for me, and I will be accepting and reading the questions.